Good day, everybody. We are going to be presenting the molecular dashboard of the SAPCS, the Southern African Prostate Cancer Study dataset. Patient-level molecular driver visualization and aggressiveness profiling is the study title. African ancestry prostate cancer is clinically important but genomically underexplored. This on its own creates a need for tools that translate complex molecular data into clear patient-level insight. So what is the problem here? The problem is that the SAPCS data includes driver gene subtypes, signature pathways, and clinical markers. Interpreting them is a difficult task. Objective of this study is to build dashboard that links molecular complexity with disease aggressiveness and patient-level risk prediction, with the aim of turning complex prostate cancer DNA data into a clear dashboard and bring together gene mutation, cancer subtypes, pathways, and patient risks so that we can better understand aggressiveness in the Southern African prostate cancer study cohort. So the dashboard objective is to visualize driver mutation and molecular subtypes, summarize mutation burden signatures and pathways, explore association with disease aggressiveness, present a patient-level risk summary, and inference new patients. So we started with project scoping and exploratory data analysis. Then we developed models and validated them. Then we ended up with a final dashboard with patient-level scoring. We had 5 layers that we integrated. Clinical markers is the first one that was with the aim of to define disease aggressiveness. Then we did somatic driver gene to show tumor-related DNA change, global mutation subtypes, to group patient by molecular patterns and mutational signatures to capture DNA damage processes, then oncogenic pathways to translate genes changes into biological functions. Then we ended up choosing the best model, which was LESO, logistic regression, with mean area under curve of 0.768 and a balanced accuracy of 0.723. And we tested it with per block, and we see that aggregate did best per block, better than other blocks, and the PSA ranked highest in feature important and bootstrap testing shows also the moderate predictive signals. Thank you.
Hello, my name is Casper, and I'll be taking you through the rest of the presentation. I'm going to be touching on the integrated dashboard that we developed, which is a tool that is meant to help the clinicians make better decisions, easily make decisions about the patients and the cohort that they are looking at. So here we've got 113 patients of African descent, of which 67% are classified as high-risk patients. Okay, so our dashboard has 7 tabs, starting off with the first one, which gives us an overview of what our cohort looks like. And here it summarizes some of the key metrics and statistics of the current cohort with different distributions and variations, distributions of different variables within the cohort. The second tab continues visualizing the distributions of some of the key and most prominent variations, which include the global mutational subtype, which classifies the different patients. We see that patients from different regions and of different ancestries fall within different patients, within different GMS subtypes, and certain subtypes are more prone to high-risk disease. Here we also see a heat map which summarizes some of the key metrics within our data, providing the median of the different metrics across the different GMS subtypes. Here the next tab, we see an oncoprint, which is a diagram that is designed to help us visualize the different types of mutations in the patients, and it will make it easier for us to identify which types of mutations are affecting which patient. The next visualizations, this one just shows the frequency of the top 20 driver genes, while the next one is just a heat map that shows the co-occurrence of different genes within different patients. The next tab visualizes the molecular burden across the different ISUP grades. The first one just is a plot which just helps us identify the range and of the different, which just helps us identify the range of the data for each ISUP grade. The same for the percent genome altered and the tumor mutational burden. Here we've got also per patient mutational burden, which helps us visualize the counts for each of the patients of each of the mutational burden. Here, the next tab is a heat map, which shows us the signature exposure of the different patients to the different signatures, where we are using color coding to visualize higher extreme exposures to the specific signatures. And we've got pathway alteration as well, which helps us to visualize the alterations of the pathways within the different patients. The next step helps us to visualize if there's any statistical evidence linking drivers to aggressiveness, where the further the driver appears on the plot on the right from this line, which is the neutral line, is the more that driver is contributing to aggressiveness, where the further it is on the left is the one is showing us how much that driver is deducting from aggressiveness. The last tab is the independent patient scoring tab, which just allows us to select a particular patient, and this will give us the opportunity to visualize independent metrics for that patient and see which of the drivers are contributing to the particular score that they got. If it's high risk or low risk, this will help us visualize which particular genes are contributing to that. And then here we've got the single base signature exposure values, which just shows us the amount of exposures for each of these substitutions. So here we've got some key findings. That first thing is that this research is mainly for research purposes only. The data set that we used is not conclusive enough for us to come up with the final result which we can deploy, which can be deployed clinically. And the next step would be to probably, if we can get more data, this will allow us to train a more statistically robust model, which will be able to pass validation for real-world deployment. And with that, I say thank you.